Okay, so this is electromagnetic induction video 2. We hope we'll get through this one without interruption. So in video 1 we learned that to upload to YouTube you can't go over 15 minutes. We went 17 minutes. So that was a little bit long. We need to be a little bit quicker. This is going to be even more gonzo than the first video. Because I'm going to show you some notes and then we're going to try and explain how or why those little experiments worked the way that they did. Okay, let's have a look. Now, there are notes that go with this lesson. If you were here, I would give you the notes. Since you're not here, I'm going to send them to you by some means. Okay, here's the note that you would have written up on the experiments that we just did. Here's the wire and the magnets. And what did we do? Well, when we moved the wire into the field, then we got a small EMF induced in the wire, which we saw as a current on the galvanometer. However, if we hold the wire at rest in the magnetic field, we get no EMF. So you only get an EMF when the wire moves. If you remove the wire from the field, we also get a small EMF, but it's in the opposite direction. If we move the wire more quickly, the EMF gets larger. We didn't see that. If we reverse the field, in other words, if we turn the magnets around, then that has the effect of inducing the EMF, but also in the opposite direction. And we didn't do this either, but if we keep the wire still and move the magnet, that also produces an EMF. So the point is that you don't get an EMF unless there is motion. And it doesn't matter what moves, the magnet moves or the wire moves, as long as there is relative motion. Now, our second experiment was the magnet and the coil. So we had a coil of wire, we had a magnet, we moved the magnet in and out of the coil. When we move the magnet into the coil north pole first, an EMF is induced in the coil. When we hold the magnet at rest in the solenoid, we get no EMF. Next page. If we remove the magnet from the solenoid, we do get an EMF induced, but it's in the opposite direction. Move the magnet more quickly, gets you a larger EMF. We had trouble seeing that. If we turn the magnet around and push the south pole of the magnet into the coil, we get an EMF, but the direction is reversed. If we keep the magnet still and move the solenoid instead, we get an EMF. So again, the EMF is induced when there is movement, but not when there is no movement. And it doesn't matter whether the conductor moves or the magnet moves. The third experiment is even more mysterious. We had two solenoids. So we had two coils close to each other, but not connected, notice. They were both wrapped around C cores, or there was an iron C core present. On one side we have a battery and a switch. On the other side we just have the ammeter. Now, when we connected the magnetic field solenoid, this one, to the battery, then an EMF is induced in the second solenoid, and we saw the needle flick. If we leave the field solenoid connected so that the current is flowing steadily in this coil, in this circuit, there is no EMF. The EMF is only induced when the current is switched on or when it's switched off. When we disconnect the field solenoid, an EMF is induced, but in the opposite direction. So when we switch the current off, then we get an EMF induced in this side, a quick flick of the needle. Right, we didn't go on to this part, but if we add more cells to the battery, we get a larger EMF. If we have more turns on either coil, if we change the number of turns, that also affects the EMF. Okay. Now, what conclusions can we draw from this? Well, there's three. First of all, that we get an EMF when there is relative motion between a conductor and a magnetic field, or when there is a change in the magnetic field around a conductor. That's experiment 3, as we'll see. The size of the EMF is proportional to the strength of the magnetic field, the rate at which the wire or the coil moves, and the number of turns on the coil. And the direction of the EMF changes if the direction of motion is reversed or the magnetic field is reversed. Okay, from that I hope you're getting a bit of a picture of how electromagnetic induction works. Now we'll try to explain how that is actually happening. So can we model what's going on here and try and explain it in terms of what we know about magnetic fields? Okay, here's our two magnets. We know that there's a magnetic field in between the two magnets, and we can represent the magnetic field using pieces of spaghetti. Okay, so here's a piece of spaghetti. If we break it into pieces like so and place the pieces across like that, they can represent the magnetic field lines. Okay. Now, magnetic field lines between these two magnets, it's more or less a uniform field with the field lines running north to south. Okay. Now, in the experiment, what happens is that, let's move the camera back a little bit more space. What will happen is that when this wire moves down through the magnetic field in between the magnets, then we see an EMF induced. Now, we can explain what's happening if we think about the magnetic field lines. When we move this wire down, what it's going to do is it's going to break through these magnetic field lines, or we could say it will cut them, like so. Okay. Now, when the wire is within the field, it's not going to cut through any magnetic field lines. But when we remove the wire from the field by lifting it up again, it's going to cut through the field lines again and break them, like so. Something like that. Okay, now this actually gives us a way of understanding what's going on. We say that when the wire, the conductor, cuts through the magnetic field lines, the magnetic flux lines, then an EMF is induced. When it doesn't, no EMF is induced. So when the wire moves into the field, it cuts the field lines and induces an EMF. When it's at rest in the field, it's not cutting any field lines, and so no EMF is induced. When it is removed from the field lines, it cuts the field lines and an EMF is induced. But because the sense of cutting is opposite, it's happening in the opposite direction, so the direction of the EMF that is produced is reversed. Okay. Now, that at best is a partial explanation. Okay, because we can't say why cutting through field lines is going to lead to an EMF, but at least we can link the idea, our model of a magnetic field as being made of flux lines, to an EMF being induced via this idea of flux cutting. Okay, now if we look at our second model, or our second experiment, which is the coil and the permanent magnet, well, can we use the same idea here? And the answer is we can. Okay. Now, for this we need more spaghetti, but the spaghetti really needs to be cooked. And things being what they are, I can't quite manage cooked spaghetti. So, we'll have to draw the field lines. Now, we know that if we have the magnet, we know that the magnetic field lines extend out from the magnet something like this. Okay. I won't put the directions on them, but we know that the field lines are there. Now, if we move the coil towards the magnet, what we'll see is that here are the field lines coming out from the magnet. As the magnet moves in, can you see that the turns of the coil are going to break through or cut through the field lines? So, for example, when the coil is about here, it's going to cut through this field line and cut through this field line. If we bring it even closer, it's going to cut through this field line and cut through this field line. As we move out, the coil will cut through the field lines, but in the opposite direction. So, to recap, as a coil moves in, the turns of the coil cut through the magnetic field lines. And then an EMF is induced. When the coil is stationary with respect to the magnet, no field lines are being cut and no EMF is being induced. When the coil and the magnet move apart, then field lines are cut, but in the opposite sense, and so an EMF is induced. Okay, now, so that's using the flux cutting argument to explain what's going on. Now, of course, if we move the magnet instead of the coil, the field lines will move with the magnet, and we will have the same effect as the magnet moves into the coil, so its field lines will be cut by the coil, and the same as it moves out. But if the magnet is held stationary with respect to the coil, no field lines are being cut and no EMF will be induced. Now, every turn on the coil can cut a field line, so therefore one field line may be cut many times by each of the turns in the coil, and that's going to result in a larger EMF. Okay, now we're at 12 minutes. What we want to explain now is the other way of looking at this, which is a slightly more sophisticated model. So another way that we can describe what's going on here is in terms of flux linking. Now, the way that flux linking works is like this. We know that every flux line that we draw is in fact part of a loop. So it might be quite a small loop, like this one, that goes around from north to south. It might be a larger loop, which goes a bit further, but still goes north to south. This one, that we've only drawn part of, nevertheless keeps on going all the way around and comes back to the South Pole. It's a loop. Now, likewise, the turns on the coil are also loops. Now, when we move the coil towards the magnet, when the coil cuts through a flux line, we can say it links it. It's a little bit like the magic trick that magicians do with the rings, when they get two rings and they clang the two rings together and they magically link together. So we can imagine that if that's the loop of the coil of one of the turns of the coil, and that is the loop representing the magnetic field, when they come together, the two pass through each other and become linked together. So now the coil, the turn on the coil is linking, it's trapping one line of magnetic flux, or one loop of magnetic flux, like so. Okay, now if we move the coil in, then what will happen is that many lines of flux will be linked by each turn on the coil. So we say the amount of flux linkage increases. We can quantify that. 50 seconds to go. If the coil is here, then maybe only one line of flux is linked by the coil. But if we move it to here, we can count 1, 2, 3, 4 lines of flux that are now linked by the coil. So moving in, flux linkage increases. Moving out, flux linkage decreases. Now, I hope you can see that the idea of changing flux linkage is just the same as flux cutting. Quick stop.